Good. I think some people still missing, but I guess we can just start with the question time for our with our two speakers, Mary and Olga. So please, we can open to questions. I remember that there was a pending question by Alessia to Mary.
I was wondering, like, we are what look at deviations. What look for correct picture. No, that is in sense model independent because I mean if you
yeah, but then
right, you get the
so
logbox are tabs and this should be like
what kind of effect you are looking for? So that's for me how, if you tell me how this is going to modify the waveform, then I can tell you if it's so. I need to know what exactly you plan. I mean, what kind of modification you're thinking that it's going to be. If you give me the modification of the waveform, then we can put constraints. Not that I know of, but you know, the important question, yeah, I mean, you cannot do it blindly there. That's what I mean. So it's not an independent kind of test. So I would now, if you give me the modification of the waveform, the amplitude or the phase, what do you expect? And then we can see how this could depend on the redshift from where it comes to you that you receive it. Then we can see whether this is reachable or not. Okay. But you had a question, you said for Olga as well? I'm sorry, I misunderstood.
Alberto?
About this mini superspace ansatz. So the mini superspace ansatz, basically what matters in the measure is just the scale factor, if I understand correctly.
And it depends only on one direction, doesn't depend on the transverse.
You basically say that the metric is...
I saw, exactly, yes.
So I was wondering how under control this ansatz is, because in the path integral you have integration of all possible metrics, including inhomogeneous and isotropic.
Exactly. When you do this, you don't take into account all these contributions that you said, and that was my comment that you could say that all these things are very simplistic. You can say this also for the no boundary proposal, and to have a UV complete theory, you need to take into account everything, and then you need to be very careful how you perform your path integral, and probably you need to do this Picard-Lefsetz, use Picard-Lefsetz theory, so that you know you go to the complex plane and you do it mathematically correct the analysis of your functions there, and you pick up an appropriate contour. And these people are studying now, but we didn't do that.
The superspace would have to be thought of as a toy model rather than an approximation. That's not correct.
Yes, the idea was to see if in this simplistic model that you only take into account contributions from isotropic and homogeneous spaces could give you something reasonable, interesting, and relevant for the early cosmology of the universe. So yes, you could also say it's a toy model, but yeah.
Paolo?
I don't know if I should do like you. I know
Yeah, indeed. So just to remind everyone, for new questions, we raise the hand. For follow-up, we raise the finger, the proper finger.
So it's I agree that doing the Picard-Lefsetz will surely will highlight and enlight what you have done. But I have perhaps one suggestion which you might consider is less used, but perhaps simpler, and it was used by Halliwell and Hartle, which is using the Kantowski-Sachs model. So Kantowski-Sachs is not so complicated as the Bianchi-9. He has already some difference from the Friedman model and we could compare what you might get in your proposal with what they have got given the no boundary for Minkowski size. So yes, some anisotropy as well. And to my knowledge, there are wormhole solutions that exist. They have been found by Garay and others many years ago for a Minkowski size wormhole. So that's something. The other thing, which again maybe you don't have yet to result of, it's when you put the action field, how would the charge of the action itself would present it in your wave function, the implications for the perturbation? So would it still be scaling variant? Would you find something you have not?
We haven't done, this is exactly the third bullet in my future directions, that we want to study all perturbations, right?
Small charge or something.
Yeah, I mean, we have computed that the on-cell action, if you choose a small charge for the action, it's positive and gives these nice results. But
falsifiable, like in ions, if you do something for perturbations and you put the action charge or field, and you are getting something that is not totally according to what we observed, that it will be a severe test.
That's true. Yes, I agree.
I'll be waiting.
Sure. Thank you.
Questions or comments? No? Otherwise, I will ask something. Antonio, you moved your hand. I don't know if you had that question.
No.
Okay. So I've actually both, since we were with Olga, we can continue with Olga. I'm not very familiar with this approach, but you start as a boundary, you start with an Euclidean anti-de Sitter, which will have some negative cosmological constant. But to really go to the cosmology that you observe today, do you need to fix some value for this negative cosmological constant, or you have lots of freedom on it? Like you can just use it as a free parameter there.
No, you don't need to pick a value. You have, I mean, this all depends from the specific model, what will be the specific potential. I just gave generic conditions that the potential should have, so that it will be possible to indeed pass from negative to positive values, but exact values of the cosmological constant and etc., they depend on the specifics of models. And
so whether you start with, I don't know, very large negative lambda, very small negative lambda, you will still be able to anyway go to this.
Yeah, with the
cosmology
appropriate relevant deformation, you will be able to.
You just need some negative potential, which become positive. That's the only thing.
Yes.
I see. And in general, this is a more general question. Like when people start.
Sorry, coming back to that. I'm sorry.
Sure.
That means that if
Microphone.
you might
I'm
have,
sorry.
so probably the fine tuning might be much more important if you start, for instance, with a large negative value, no, so that it's not as innocent as it's.
So if you want to do this, what I show you, for example, with irrelevant deformations, then there is a lot of fine tuning. But with relevant deformation, I think generically, yes, you can go. Yeah, there might be special values that you cannot do it, but the general idea is that, yeah.
Okay, so yeah, my more general question was, you're starting, I mean, it's fine, you're starting from some ADS, but you really also have some Euclidean ADS, which means that on the boundary there is no concept of time, in principle. So in this picture, is like time emerging in your framework?
No, I
not?
wouldn't say that it emerged, because it's not like I started with 3 dimensions and then the fourth dimension is time. I have 4-dimension Euclidean ADS, and I just analytically continue what was the radial direction to time. So I wouldn't call it emergence in the sense that some extra dimension pops up, like in a holographic setting that you have the CFT that is 3-dimensional, and then you have a 5-dimensional space-time, for example. Sorry, 4-dimensional if you have 3-dimensional boundary.
Okay, I
yeah.
see. If I may ask to Mary, unless there is, okay, Ben.
Following up on that, what is the physical mechanism that brings you from the Euclidean to Lorentzian?
You can write down such potentials that they change value, and the way to do it here is by relevant deformation. This would do it because it's nice in holography, but you could also have some potential that change value from negative to positive.
I think mathematically, I'm saying you have some Euclidean universe. What is the physical thing? I mean, at some time, well, whatever that means, it has to flip to the Lorentzian, right? Because we live in Lorentzian signature.
Yes, and this happens because the value of the potential.
Is it a phase
It's some
transition?
tunneling.
Phase transition would be something like
It's a nucleation distance, exactly. And with this proposal, instead of nucleating very low, as is the case with the no-boundary proposal, that doesn't, so slow roll inflation, for example, it's not described by the no-boundary proposal. Here you have the extra feature that you go up in the potential, so you can nucleate higher up and you can have inflation, because as inflationary models are now, you go and put this value by hand that you are high up in the potential to be able to have inflationary theory. So it's like an instanton. You have a nucleation there.
But nucleation would suggest some time evolution, right? And what is this time evolution?
I
don't think I understand the question. Maybe
I
you can
think the question is, what is the physical explanation, the physical mechanism that can make the change of the signature?
Exactly.
Not from a mathematical point of view, but what is the physical process that could lead to a signature change? No? That will give the arrow of time at the beginning of the time. That's the question.
Okay, but this is, I mean, for the no boundary proposal, what you would say is the answer to that. I would say it's the same thing, right? You have a nucleation, so you have an instanton, this formed, and
to mention another context in which you have an answer for this.
okay.
So in quantum cosmology, at a certain point, people observed that there was something that looked like a Euclidean phase, very close to the Planckian energy density. So what was happening was that when studying the propagation of primordial fluctuations, at a certain point, very early, they were behaving as if they were propagating on the Euclidean space-time. And I think the explanation of this, that is something you see very clearly in the equation, is simply that at a certain point you reach a region in which you have non-perturbative quantum gravity, and therefore you have superpositions of metrics, superposition of geometries. So effectively, you don't see any more just one Lorentzian time direction. And this is what I was mentioning before, that even when you do the integral version of the quantum gravity form, you compute the transition amplitudes, everything is fully Lorentzian, but then you have this region in which you need the contribution of non-Lorentzian geometry, namely Euclidean geometries, in order to have a tunneling process. You have to wait into the path integral those contributions in order to have this tunneling. If you don't do that, you can do semi-classical perturbative calculations, but you cannot account for a tunneling that is in perturbative effect.
How would the little bit just
No, I didn't have any comment. I just rephrased his question.
Let me just say, it's, correct me if I'm wrong. So when you have field theory, you can have a transition where the vacuum and stellar something emerges. Tunnel has nuclear, so the vacuum and stellar there is a probability. So that is much more complicated when gravity is spread, because this involvement comes. Even discussing the time issue, that's not just an issue, it's the issue. Time, there is even a book by Halliwell, who wrote it with many contributions, which is called the time hero. So it's still an open game, an open quest. Even in quantum cosmology, I might just add a little bit of complexity. Again, means you can have what we call the WKB time. You can have different WKB times and many finger time. These words are concepts that were even introduced in the 60s and in the 70s by Wheeler and Dewey, because they were already facing the difficulties at the Hamiltonian level. So, but coming back to this, I would say that if you consider that you have something of instantaneous, some nucleation, the universe will emerge with a finite later, like in plain quantum mechanical field theory, that's what you grab as a working hypothesis to make predictions if it works. So it is shaky. It's not so frail as some people might think, in my opinion, but they can have a different opinion, of course. And it allows you to make predictions that you can check. So far, both the no boundary and the tunneling and other linears, the Picard-Lipschitz and so on, they have produced remarkable, interesting results. I might be wrong, but I think this Picard-Lipschitz approach is mathematically rigorously, but it needs to be further explored. So it's a 21st century discipline, quantum cosmology, in my own opinion.
But I'm sorry, but this, what does it have to do with this question?
Yeah, just making
question.
a comment.
Oh, that's a comment.
I think,
Okay,
for
fine.
the question.
The scope to get the quantum contribution.
Okay, thank you. I do have a curiosity actually about
Okay.
gravitational waves. What have, as you said, right? What we have been observing so far are gravitational waves from binary systems.
So far, what we have, yes, but as I said, no detection yet of a gravitational wave background already
Right.
can put constraints in theories which
Right.
predicts X, Y, Z.
And my question is more like about just astrophysical sources. And it's nice because you mentioned at the beginning there could be like a persistent gravitational wave signal, for instance, from a spinning neutron star. Okay. Or one could see also gravitational signals from a collapsing star in principle. I don't know. So what is the current hope to basically be able to see gravitational waves, astrophysical sources that are not binary correlate
People are
images?
searching for them. In the collaboration, there are groups searching for them. It has not been found yet.
Is it very far?
It's the point is that it is how do you detect them, and it is much simpler to detect what you know from measure, because then you can have you can calculate what will be the waveform. So you have a bank of waveforms which detect which depend on the parameters. If you talk for compact binaries, since the mass of the spin, and you try to see what fits better. If you do not have a really very good waveform and you are more blind, then becomes more difficult. But there are indeed groups which they do the searches. For instance, supernova, they try to do so. So there is an active work on that now. When they're going to find or how they're going to find this, I don't know. But this is something that goes on.
And are there already like templates for this?
There are templates,
thing?
yeah.
Okay.
There are templates. There are several templates which depend on the astrophysical model that you are going to have, but there are templates. Yeah.
I see.
There are templates, or you try to find, if you know what the noise is, then you can try to see whether you find something like you know, a kind of peak that you are going to have, which doesn't look like a noise, and then from there you can to see whether you can map it to some kind of model behind. So that's, but it's of course more difficult.
Okay, it was follow-up by Stefan.
Before LIGO started to see things, I remember that there was a lot of expectation to also see an isotropic collapse, core collapse supernova. And we haven't seen none. So my question is, what is now the interpretation of this? Is the model of
Yes, the model of the core collapse is not what they were expecting, because the astrophysical model is the same thing. Like they never thought that they're going to see that many binary black holes. That was extremely new, and so the thing is probably the models that were behind were not physically, or not the best, I don't know how to phrase it. So yeah, the idea is the astrophysical kind of modeling has to be.
Is there anything else that they are actively searching for?
They are searching, I mean, actively search is for continuous background. Okay, that's an active search. Then the stochastic background where I'm involved is an active search. And then, you know, the supernova kind of thing. So there are groups dedicated in doing that. It was surprised that everything that came so far was from binary black holes at this mass range. But that means the astrophysical models were less reliable than they were thought before.
I clearly remember a book where we were saying we were going to see mainly neutron stars.
That's what everybody believed, and we just saw a couple. Yeah.
Questions or comments?
Now it's from this is from my own period. So taking just 4 dimensions, that brought some questions a moment ago. So modified gravity is still possible?
Well, the modified gravity is not going to give me extra dimensions. Well, I don't know. The models of modified gravity that I know of, there are in 3+1 dimensions. So I don't know of a modified gravity which is more than 3+1 dimensions, unless you have one. You know, I take the modified gravity models that exist in the market. I don't know any of them that is in more than 3+1 dimensions. If you know one, then we could.
No, I'm thinking of 3+1 dimensions.
Okay.
What I'm thinking is, okay, so you change substitute in your equation. So it's still 3+1.
Why do I change my equations? You said you change something.
Because I want to get fun and I want to change.
I cannot change my equation as I wish. So the equations are going to be derived from the model that I have behind. So in my starting point, I have something that goes beyond GR, and therefore the equations that I take for the tensor modes are different than GR. So you have to tell me, what do you change?
I'm about to read it's plus, but I'm a discrete person.
You're what?
I'm a discrete person.
You're a discrete person.
I'm not
No, continue.
I try not to. So, but what I was planning to do, just for fun, is to, in the wave equations that have gravitational waves, is to consider, just for fun, because I can and I want to, fractional derivative. This is something that has been done since Riemann. And my point is, okay, since gravitational waves is the new astronomy for the 21st century, it has indeed allowed us enormous discoveries and checks. What if I, instead of in the Lambertian, as a second order derivative, I put something that can have a fractional order? So this is something that has been done.
Yeah, but look, for me, I don't like to change ad hoc an equation. The equation is,
Okay.
then I can give no answer, because for me, the equations are derived from the action that you have.
My question, what would be the smoking gun? You show polarization.
I don't know, and I'm not doing random things, so I cannot give you an answer or any comment. For me, an equation of motion is not something that I have the liberty to write it. It's something which comes from an action. So if you tell me what is the extra ingredient that we'll put in your action, then probably we can discuss. But otherwise, you go blindly. What are you looking for? So this theory has to tell me whether it predicts that there will be a mass of the graviton, which there will be massive. It's going to, what this theory tells me, just mathematically to play, to take an equation, change the derivatives.
Special relation.
So then you tell me how this is. So you have to go back in when I wrote the phenomenological part of the dispersion relation to tell me in which these 3 parameters alpha and A correspond, because I have an extra term. Then I have constraints which I gave them to you. You have to go map to your equation and see to your.
It's not that you have to your action, but it is really a modification at the level of the simplest kinetic term. So you wouldn't have something like p squared, but you would have something different.
You think of the essence or something like the essence.
I don't know.
My point is that when you do electromagnetic, it's through a wave equation, right? Allen-Bertin is there. If you put a fraction, derivative there, you
Then
get
you don't
different
have-
thing, you
don't have
get
square
different
anymore,
transmissions
but
for.
No, but it's not that there is an answer, but it's very model dependent. The observation that you can look at. Of course, if you find extra polarization, so with respect to what you expect in gravitational waves, that to me it would be a very strong hint that something is going on, that you have extra degrees of freedom.
But you will say there will be it will induce somehow.
It will tell you that there is a class of theory that maybe, imagine you find a longitudinal mode. Normally, this is what you would expect if you have a scalar degrees of freedom.
It's
Yeah, but
related
what he
to-
says, he doesn't have an that's why I'm asking, what is the physical ingredient that you will put there? Then we can see what could be the effect. If I don't know the physical ingredient and just we take the question, you change it,
But if you see an effect like an extra polarization, there are many theories that
for sure. I even said that.
the waveform.
Yeah, that's.
Derive the black holes in that theory, look at the waveform and see.
And then, first of all, you have to see if in your theory you have a solution which is a black hole. Whether this is a stable black hole, you have to calculate there how the merger will be before you go. So I think there are all these intermediate steps that if you don't know, I think you can do it, but I believe it's very dangerous to try to see. Let's say you find what are you looking for? How you interpret what you find? I don't know.
No, just make a comment.
To say that when I'm in Paris, this is just a minor comment. Allow me. So when I'm in Paris, I've been there many times. My family. I go to the Pompidou, so I'm always shocked with some allegedly works of art, but they just do it because they want it. So,
But that's a dangerous thing to do something because we can do it.
I'm not using any massive destruction bomb. I'm just putting a derivative and see what comes about. But nevertheless, if I can and if I will put on the archive and then people can comment on that. So, but nevertheless, thank you so much.
Just to make a comment like useful for your question. I don't know why people do it, and I don't know if there is some motivation, but you can get some fractional despeciation for a gravitational wave if you choose some function here, which have some like fractional power of the box Allen because this will affect the propagator of your spin 2, for instance. I don't know why, what are the motivation, but you can write down from a Lagrangian, something like that. Yeah, I can give you the right paper. There is a right paper.
Well, as for motivation, if we have here exponential something like this,
that's something different.
Is to obtain a normalizable theory.
Yeah, but that's not related to this fractional things. It's something else. Yeah.
So,
please, Stefano. Sorry.
Yeah, it's a related point. This discussion is okay, but there is something provocative that I want to say, and then you tell me if it's not, if it is too pessimistic. You know, there is this joke about the policeman that see a guy looking in the night, drunken guy looking on the ground below a lamppost, and say, "What you're looking for? For my key." I say, "Okay. Where did you see the last time?" I was like at the pub. So why you're looking here? Here there is a light. So the point is, and this is more a kind of, can we really say that we are not? I mean, we are looking when we look at waveform. We are comparing. It is very difficult not to extract the signal. We have waveform, which are first of all the one which we're working are produced starting from GR. So we are, in a certain sense, it's a bit like in cosmology. You maybe were writing exactly this case yesterday. So in cosmology, we interpret everything with the lens of GR, and then we say we add the lambda CDM, but somehow there is an intrinsic bias from the start in the way we extract the physics from the data. Isn't a bit the same the situation now? We are really at the
I agree with you. There is a kind of, let's say, bias. That's why some of the cases that you say, I want to see how the result would have been different. That means I start by the calculation of my waveform in this new theory. But then you have to, again, to see. Now, the point is, I agree with you, but the point is that up to now, the majority of the data we had are nearby, which means the redshift is small, and therefore you would expect that what we know locally could still be valid. Now, otherwise, what we do, indeed, we allow in the theoretical model and the way we map it with the data to allow for a mode, for an H, an amplitude which is going to be modified by this different theory. So you have to, so either you try to find something generic, or you start with your theory and say how my waveform would have been modified. Can I see something once I extract the gravitational waves from GR? If GR is correct, as I said, what you see, it should be just noise. If it's something which is different than the noise, which I can calculate it, I know what is the noise of my instrument, then could be hinted something beyond GR. So that's the way that you do. I think was something big.
Yeah, just comment related to this. Yeah, might be a good comment, but I would say I understand what you say. If I just modify the way the question for the gravitational waves, introducing some fractional differential operator and so on, and then you don't have the action that generates that stuff, then I understand that you say I don't even know how like my interferometer would work, which are the new degree of freedom line.
No, I didn't say that at all. I didn't say that at all. What I said, let me repeat, is that me, personally, that's a personal point of view. I don't like, in an ad hoc way, to take an equation and modify it without knowing why I modified that way. This is a personal view. Somebody else can come and say, for me, it's like everybody came with the dark energy models, ad hoc they modify, and then they work with that and they happily live. For me, I don't like that. So I don't know, I don't like in an ad hoc way to mod. I'm not saying how my instrument is going to do. My instrument knows how it's going to do.
Okay, but like, maybe I misunderstood, but you say something about the thing, you will not be sure what you are looking for in that case if you don't have an action.
No, I just said there are two things. Either blindly you change your equation and you try to see, I compare that with the data, what is the difference? And then, of course, you don't know how to interpret that. What does it mean?
Okay, this, okay, kind of, I see the problem, but then if you, okay, the gravitational waves are, they are related to the linearized equation and the what you get from this kind of linearization of population. But if you, so you don't give only the fractional differential operator for the gravitational waves, but if you give also the modified Einstein equations, okay? So you still don't have an action, but you have the full modified Einstein equation. Then you linearize them and you get hopefully you get.
Look, I don't know. Here okay, here is.
I'm just arriving to the question, and then you get that fractional D'Alembert equation for the gravitational waves. If in the modified Einstein equation you are at least able to say this is my matter container in the stress energy momentum tensor, and this is my part of the stress energy momentum tensor, which is due to the new gravitational degrees of freedom. Even if you don't have the action,
No, look, okay, forget the action. I mean, I would like to know where it comes from, and I would like to know what are the kind physical signature of something new there. That's what I said. When he said, I can do that, and I want to enjoy, I don't know, to have fun. I change this, and I do a fractional kind of it. What can I do? I said, fine. I don't know what I'm looking for. I don't like doing that, but anybody, so it's not a criticism. It is me. I don't like doing that, so I don't do it. And I would like to know what I'm looking for. If somebody else wants to do it, you put it in the archives and then you see what comes. So it's you know.
Just to stress that why it's so difficult to do it. I mean, as long as eventually you abandon GR, you have some other theory of gravity, for example, fourth order field equation. If you have fourth order field equation, firstly you want now to go to LIGO. What you have to do? First of all, are there black hole in this theory? So you start to say, okay, let me take a vacuum solution to start with, and then see if there are black holes. You find a black hole, congratulations. Normally, when you have higher order theory of gravity, there are just the simple black hole of GR, there are no solution, you have to pick up one, okay? Now, once you pick up this black hole, you want to do, I don't know, quasi-normal modes. Quasi-normal modes, normally you have to start the gravitational equation, and then eventually, let's assume you are in vacuum, then you do quasi-normal modes, but you're not dealing with fourth order equation. Fourth order equation are not as simple as to work with. And imagine if you have a non-local gravity. That is even worse. And I mean, in the sense, it's more difficult, technically challenging.
Yeah, it's technically challenging, but as I said, I agree. That's why I said before, you have to see that there are black hole solutions, that there are stable to calculate that. That's why it doesn't happen, because you see, it is such a huge effort, so many PhD theses in doing that, probably for nothing. Unless you come and you tell me that this modified gravity, it comes from this kind of I don't know, quantum gravity approach that ever passes already some test, then I will put my student to do it. Otherwise, it's so much effort for nothing. I even mentioned before that the quasi-normal modes beyond GR, you cannot do it because the separability equation, the Kolsky equation does not hold anymore. You have to include spin there. You don't know how to do all these things. So you can do this enterprise, which is a huge work for many, many poor PhD students for something that then you might be the dustbin because this model doesn't come from anywhere. So that is why I think that if you want to do it properly, you have to start from the beginning all the way down. And that is a huge amount of work that only if it is consistent, theoretically justified, and already passed some test, it has to be done. Otherwise, I think that is a work that, you know, so if you start in the middle of this whole path to do your calculation, I'm not sure whether you probably waste your time, because tomorrow somebody comes and said, hey, you know, this kind of black hole solutions does not exist here. Then what have you achieved? Nothing.
I completely agree. So unless the approach is well motivated, don't waste your time.
Okay, to that there is a paper by Javier Calmet. It is called The Free Waves from Quantum Gravity, and I mean, it is in a particular setup where you have only a quadratic action plus for-loop corrections. And in that case, since you have the two additional modes, I mean, you have the ghost and the scalaron, then it turns out that your wave is modified. Actually, you have like additional waves that are propagating. And since quadratic gravity is, you know, many people work on that, that would be one thing that we eventually test.
There are examples of well-motivated theories, not that there aren't.
Yeah, there are.
The problem is that as you leave GR to connect with, I mean, you really need the tools to because if you don't have care, if you don't have this separability, in some theory you don't get the character cost and you don't know how people stuff, even to reproduce the orbits, to reproduce the shadow start to be complicated because
you not integrated. But I just know that there is this paper and did not check like the calculation. So, but if the result is stable, then because it's like modification that you...
Yeah, but then they have to do all the steps.
Maybe maybe there is another way, no? But maybe let me be. Maybe we should do what it was done with post-Newtonian approach for solar system test, and that develop some kind of systematic way to parameterize deviation from GR in the regime which are now interesting for us. So maybe far infrared for cosmology, or the regime where you are in a situation like a black hole merger. I mean, maybe that another way to go is to have a kind of suitable parameterization of the deviation instead of picking up a particular theory, work everything out.
Yeah, no, you can do it. That's why you can do this thing of trying, and this goes along the way of this kind of post-Newtonian kind of approach, or PPAE as they call it. So yes, you can try to find, but then the difficult aspect is to go and interpret what you find for a particular theory. So that's the difficult task, which remains open. Yeah, that's the gap. But there are all these tests in this way that people do. I mean, but there's
I have a comment rather than question, which is in particle physics, this sort of question is being addressed because of the main task nowadays is trying to find something wrong with the standard model. And the traditional approach to that is to think up something that could be different than the standard model, and then go look for places where you might find deviations in experiment. This is very hard, and it tends to be unproductive. So there's actually a modern information technology-based approach, which is totally different, based upon the fact that this is something that we don't yet have in gravitation or cosmology. But in particle physics, you have petabytes of data, which you don't know what to do with. It's just way too much. So you can reformulate the problem of training, basically with artificial intelligence, training systems to recognize events, right, and classify them without human intervention. And then you train it on large amounts of data. Oh, this is a 4-point interaction. There's a Higgs there, and so forth, and a W, and it classifies it. And then, having developed a catalog of learned experience at machine level, you then turn it loose on the petabytes and see, do you see anything that doesn't fit?
okay.
Without a question, without formulating a question, just throw it brutally.
Yeah, exactly. What you say exactly we have done. We're at the beginning with two students of mine. That was dictionary learning. So again, it's kind of categorize things. The point is that we have 2 or 3 papers on that. However, we are still as a methodology paper, exactly because we don't have many data. So we have trained that with a few data we have, and then injected data that we just produce them, But the idea is that exactly to use this methodology, the collaboration doesn't use it very much yet, so it's not very simple to to put it forward. But the idea is exactly that, but it will be used once we have many more data. And there is a meeting that will be in Canada in a couple of months, exactly how can be put forward this kind of machine learning approach.
The accumulation of CMB data and stuff, but we start to have large data sets that you could approach.
If I may add, so recently in a conference online, live, someone giving data from supernova to ChatGPT for the last one, and without telling that there were data from supernova, they guessed that there was data from supernova, organized it, and after a few iterations, he pulled out an estimation of dark energy. So that was quite amazing because it lasted the whole process for like 15 minutes live. There must be a deceleration parameter which is of the wrong sign. That's it. Just to say that it could be extremely powerful.
Yeah. We do that we try to push that forward for the gravitational background. Also because when from the collaboration we try to do a parameter estimation, it takes of the order of a day. And what we can do it in our way with the machine learning is less than a second. So it goes much faster. So we have the tool how to do it. but it's something that we need more data.
Still, it's a very good point.
Yeah.
I think that this is probably the way we will do at the end.
Yes.
My question will be perhaps less related to your lecture of today, but more related to discussion with your participation yesterday. That is, can we comment a bit more why scalar inflaton is not an acceptable field to explain the inflation?
Oh, it's very simple. I don't know of what could be the inflaton field. And I know that the Higgs field has been put forward, but to my mind, it needs quite a lot of fine-tuning of the self-coupling in order for the Higgs to play the role of the inflaton. So for me, this is a fine-tuning. And to my mind, at the energy scales where this kind that is called inflation, which I will call exponential expansion, took place, it's at the very high energy scales where quantum gravity regime should be taken into account, and that should give the early accelerated expansion. You can map this kind of gravitational kind of effect through a hypothetical scalar field, the inflaton and the potential. But this is in order to do the mapping and do your calculation of the slow roll. But I don't think that is a scalar field. Oh, models, there are thousands, yeah.
Explain how Hartle-Hawking fits into a more complete mathematical integration. But one thing I didn't say, in the end, it produces a very nice inflation. We didn't go far enough in order to do a graceful exit and all that. We weren't doing a full job there. But actually, the scalar is just coming from higher dimensions.
Certainly, I mean, in extra dimensions and in string theory, you have thousands of extra fields. You freeze all of them, and one of them plays the role of inflaton. For me, this is fine-tuning. I think, but that's my personal view, that is more of a fundamental quantum gravity effect. And we have shown that in the case of GFT, how it could work. Robert.
It's Robert and then Anna. Please, Robert.
Excuse me?
I'm going to support what you just said. So if you come from point of view of string theory, then there's a de Sitter condition which is supported by entropy arguments, which basically says that the potential of any scalar field that arises is going to be too steep.
Thank you.
Anna?
I was going to ask, perhaps Robert's answered the question already, but if you're compactifying from string theory, from M theory, is there anything in the compactification that could be the inflaton?
Yes, the radion.
I was done many years ago.
The radion looks more like a dark energy candidate than or Dilaton. I don't think Dilaton works.
Okay, so the radion is a scalar field with an exponential, and the canonical variable has an exponential potential. And that would be, that's an ideal candidate for the scalar field that can give rise to ectorosis.
Yes.
But the potential is too steep.
Yes.
Without
it's too steep for the inflaton. It could be a dark energy, but then so can the dilaton.
Yeah, but we tried to make it work for dark energy. And
so did I.
We did not, we failed.
Yeah.
We don't have a no-go theorem on that. We tried and we failed. But for inflation, it's no-go. It didn't come. I think it was in violation of the entropy. There's a paper by Gary Shu et al., which sort of derives the DS condition from an entropy argument. You need to be consistent with that.
Cool. Since we are back to cosmology, maybe we can also go back to Olga's talk. And there is one question, Robert.
What was the origin of this potential that you added to your construction?
What do you mean, from string theory? Or yeah, this is a question that I want to answer. We don't have one. So we wrote down just the conditions that the potential should satisfy so that it can lead to slow roll inflation. But at the moment, I don't know UV embedding or string theoretic embedding, and this is something we want to check. It's a bit tricky because slow roll inflation doesn't go well with string theory, and also Euclidean wormholes in anti-de Sitter, usually they break supersymmetry, so it's difficult to have an ansatz for the metric and put it in type 2B string theory and solve it. So.
Maybe a follow-up question, since you have potentials that would naturally give you something like an ekpyrotic scenario. Have you tried to embed the ekpyrotic scenario in your construction?
No, we haven't tried that, but it's a valid question and we could try to do that.
Maybe I can ask something related. So making a connection of what with Robert's talk from yesterday, and if we take to be through this Transplanckian censorship criterion, okay, then it looks like that how Robert says inflation has to rest in peace, right? But somehow you are still kind of motivating your approach from a string theory perspective, and you are trying to recover anyway some inflationary universe. So would still be consistent with what Robert said, because you are somehow generating things from a non-perturbative mechanism, or there is some contradiction between the two of you?
I cannot comment on that in the sense that I don't really have a string theoretic construction. I just have a phenomenological model. It's just that I wish that maybe I will be able to, but there are issues there. So we're not at the level of contradiction. It's way before that, I would say.
This is I was asking this question.
First Robert and then Alberto.
So calling apply here, Keshav and collaborators, they have actually been trying to obtain inflation from a non-perturbative construction in M theorem. And what they are doing is they're trying to use Glauber Suderstein scales, and which give rise to a period, a finite duration period of accelerated expansion. And the time frame which they get is actually agreement. So there is work on trying to start from string theory and to get the short wave phase. Now, I want to make this advertisement of Keshav Dasgupta's work, because unfortunately he has not learned how to write short papers. No one will read his papers, and that's what makes advertisement.
Thank you.
Thank you. Alberto?
Goes back to the previous comment. So the reason why I was interested in knowing the curvature of these solutions is precisely because, okay, as you say, you don't have a UV completion of this setup. So one has to make sure that you are in the regime of validity of effective theory. It basically requires that curvatures are small in units of the Planck mass. So I think a good check of this would be to go and see whether curvature is small.
This is what you meant. Yeah, the curvature is small. It's yeah. No. Sorry, I didn't. Yeah. This is yes.
I could, or you want?
No. I'm wondering, I mean, if you have these modifications, parameterized modifications from GR in either in the dispersion relations or in the waveform, for you, so personally for you, what would be the threshold to exclude something? So if a parameter is smaller than to...
No, I don't put constraints on the parameter. I mean, what So it depends. Either I have to find an extra kind of effect of a process, whatever. So if I don't see my data, then you know, you do a Bayesian kind of analysis and you try to see what will be the, you know, the Bayesian factor that you get. And then you can, from what the results we had so far, it was a clear threshold that you don't have it. The values were completely different. So
let's say how much is in agreement with GR.
at this point, that what we found was about more than 90% agreement with GR. So then that's why it's not something of you know, of a small difference that you can say, how do I interpret it? The confidence level was very high. In that way, you say it's out. The plots that I saw, there are more than 90% confidence level that you do.
Last question. This is more is a commentary which, given that this week is about quantum gravity phenomenology, which I think is worth making, which is related to what you say now. When small is small. First of all, it's very often the case, unfortunately, that you see constraints on dimensionful parameters, and that to me is very difficult to understand. Now, it's a big number, it's a small number. H&G units. So first of all, you should constrain dimensionless parameter, but also in that case, you need some theory that will tell you this dimensionless parameter, what is the natural value, what is the you see, when I wrote yesterday the dispersion relation, why I wrote k to the fourth over m Planck square psi, because I was basically making an assumption that that theory has a new physics at the Planck scale. Psi is dimensionless. If you find psi much smaller than 1, then you can say I pulled out already the suppression, and if you don't have a mechanism to make that small, some custodial symmetry, in your theory, then you say I have a strong constraint if psi is 10 to the minus 9. You see what I mean? So in a certain sense, it seems to me that very often the answer to your question is that it's not enough to fit, to constrain the parameter. The theory should be able to tell you what is the natural value of that parameter for that observation.
Yeah, but this again depends on the models. For instance, this was the way for which often, when you had particle physics model of inflation, for instance, take an example, and it will tell you that the coupling is 10 to the minus 10 or 10 to the minus 7 or whatever that was. Then you say this is the majority of models wanted the couplings of the order of 1 or whatever, but not 10 to the minus x. So I think that somehow I agree with you that has to be something that makes sense, has to make sense. So usually, yeah, you have to see in the theory, in the model which you have considered, what could be the order of magnitude of this thing. And again, there is some arbitrariness there because the theory per se doesn't give you this.
Theory is sufficiently sophisticated, will give you.
I mean, if in order to make the theory in agreement with what you see, you need to put a parameter which is ridiculously small, then you say it could have been 0. So if I have 10 to the minus 20, it doesn't make sense. But
I agree completely. Physical quantities are dimensionless. That we can measure. I mean, otherwise we cannot measure what are we measuring. And we need the threshold scale to know that this is something that has to come from the theory. And from the phenomenological point of view, one wants to constrain these parameters. So say, according to the data, this is smaller than 10 to minus 3. And then in your theory, you have to compute that. And
exactly, and see whether there is.
Exactly. And so it is complete unique. You must be able to compute most of the parameters. Of course, maybe some are inputs the same way you don't compute from the standard model the mass of the electron. Okay, some can be free, but most of the parameters must be fixed, and then that can be compared to the data. That's why I was talking about the deviations and what would be the threshold. So if there is a theory with a parameter, and then you constrain it to be less.
The modification. When I saw this plot with the constraints, this alpha and a, these were dimensionless.
Yes, dimensionless.
That's what dimensionless. And then I can say, and from there I know these values to what do they correspond in the modification of gravity. I take some example, and then you can see, you can go to see what is what.
Say that it's a theory that tells you there is some
Yeah.
Rating of Lorentz invariance, okay, but we know or not.
Yeah.
So if it is the dimensionless parameter that measures this deviation is less than something, what is this something for you to exclude the deviation?
As I said, I mean, if it's ridiculously small or ridiculously high, then I found it to be, so I would say more things of the order of one. But, you know, again, you have to see what it comes out. But again, you cannot rule out at this point the theory unless you go to see what will be the prediction, even loose prediction of the model that you had before. But he's right. I mean, it makes no sense to talk for things that can change depending in which scale you go. So
Okay, so I think it's the right time to thank again Mary and Olga